Good morning. Myself, Dr. Shaila Dinkar Apte, will continue with the high pass filter and bypass filter design. This is for FIR filter design. I have published the book Digital Signal Processing by Wiley Publication. You can refer to this for further details. We have already seen low pass filter design using the Fourier series expansion method, right? So I have already told you that the word Fourier series is little misleading because we are writing the Fourier series expansion for a frequency domain signal which is periodic. So we are trying to represent the frequency response of the filter as a replicated spectrum, and for that replicated spectrum we write down the Fourier series in time domain, and that because it is the infinite series, what we do is we truncate it and then we shift it because it is non-causal, so we have to make it causal also, so we shift it and then make it causal, and then we define the then we design the filter. Similarly, let us see how to design the high pass filter and the band pass filter using the same procedure. So here is one example. Design high pass filter that approximates this response, that is HDF desired response is equal to 1 between 1000 Hertz to 4000 Hertz and is equal to 0 elsewhere. That is between 0 to 1000 it is 0 and above 1000 it passes all frequencies up to what? Up to the Nyquist frequency. So Fs is 8000 Hertz, so Nyquist frequency will be 4000 Hertz. So you have to consider the frequency response only up to 4000 Hertz. That is the point you have to understand. The impulse response duration is given as 2.5 milliseconds. So how you solve this particular problem? The duration of the response is 2q into t, where q is the number of filter coefficients that you want to design. So corresponding tau that is given is 2.5 milliseconds. So we substitute it in seconds. 2q into t, t is 1 upon fs. So fs is 8000. So you get q is equal to 10. Now the filter coefficients, number of filter coefficients that you will have will be 2q plus 1, that is 21. But you need to design only 10 coefficients because the corresponding filter is symmetrical around the center point, right? So the desired response, how do we plot it? This is the desired response. HD, D represents that it is the desired response. Nu represents the frequency, that is the normalized frequency. Corresponding response is plotted like this. Nu normalized frequency is equal to 1 for the Nyquist frequency. That is 8000 is sampling frequency. So for 4000, nu is equal to 1. So for 1000, it will be 0.25. So the frequency response will be equal to 1 between 0.25 to 1, and between 0 to 0.25 it will be 0. That is how the desired frequency response will be plotted in terms of the normalized frequency. Now to find the filter coefficients, we have to use this formula. Cn is equal to integration 0.25 to 1 cos of n pi nu d nu. When you integrate, you will get it as sin n pi nu upon n pi. Integration is to be carried out. So you just have to substitute the end value 0.25 and 1 here. So you get this as the corresponding formula for Cn, and you have to calculate these values between 0 to 10. Because the corresponding coefficients are symmetrical, C of n is same as C of minus n, and you can calculate 21 coefficients like that. So this is the listing of the filter coefficients. This can be calculated as C0, it is the center value, and then C1 will be same as C minus 1, C10 will be same as C minus 10. So these can be easily calculated using the formula that we have just seen. Now this is the impulse response for the high pass filter that is plotted. Now in this particular frequency response, you see that it is causal because we have shifted it from 0 onwards. So it is existing now for Hn is existing only for n greater than or equal to 0. So the response is causal now, so it can be implementable. So you can find a filter response. So this is the formula that you will have to use to find the corresponding frequency response, that is magnitude response, and this is how you calculate the angle, that is phase angle. So phase response. So you'll find that the amplitude response is like this. That means it is constant above 1000 hertz. So because 1000 is the cutoff frequency, above 1000 it is constant, and below 1000 this is supposed to be the you can say transition width. So transition width is also sufficiently small. It is okay, tolerable, and during the corresponding interval where it is the pass band, the corresponding phase is linear. So this is what is required for performing the filtering for the speech signal. For speech signals, linear phase is essential. When linear phase is there, the corresponding, you can say the delay is delay for group delay for every particular frequency will be constant, and all frequencies will be delayed by the same amount, thereby causing no phase distortion. So this is the essential characteristic for speech signals for filtering. Similarly, if you want to design bandpass filter, suppose you consider the bandpass filter specifications as it is existing between 1000 to 2000 hertz and it is equal to 0. Again, on similar lines, we have to calculate the value of Q, it becomes equal to 10. So you will calculate 2Q plus 1, that is 21 coefficients. Again, you will plot the desired response. See, here the desired response is represented as normalized frequency equal to 1 for the Nyquist frequency, that is 8000 is sampling frequency. So Nyquist frequency will be equal to 4000. 4000 corresponds to 1. So 1000 will correspond to 0.25 and 2000 will correspond to 0.5. So the corresponding frequency response will exist and it is equal to 1 between only 0.25 to 0.5. Otherwise, it will be 0. That is why it is called as a band pass filter. Now you can also calculate the filter coefficients on similar lines again. Only here the limits will be from 0.25 to 0.5. So this will be the equation for the corresponding filter coefficients Cn. You calculate only 10 coefficients because Cn is same as C minus n. This will be same as before. So you can calculate the coefficients, and these corresponding calculations, calculated coefficients when plotted would look like this. And then the frequency plot, this see this is between 1000 to 2000, it is a pass band. So you get the linear phase, and above 2000 the corresponding stop band is there. But here the stop band, you can see that the corresponding you can say the attenuation is roughly about 25. So in order to increase the stop band response, what you will have to increase the stop band attenuation, what you will have to do is you will have to use different window functions, as we have already seen in the windowing methods. You will have to use some smooth window like Hanning window or Hamming window so that the stop band attenuation can be increased, and you can decrease the corresponding transition width by increasing the filter order, and these things will remain same as we have discussed for the low pass filter in the windowing method. So you will have to use a window, suitable window. If you are using a Kaiser window, then you will have one more parameter, one more degree of freedom. That is, you can use select the filter order for transition width, and you can use the parameter beta, which will adjust the corresponding stop band attenuation. Right. So these things we have seen, and this will remain the same over here also. Now, in these methods, what we do is we try to design the filter coefficients by considering the ideal response in the frequency domain. So we call it as the brick wall response. That means we consider that it will be straightly coming down when there is a stop band. Now, this sharp cutoff can never be obtained, isn't it? So we know that there will always be some uh, transition width. The transition width can never be 0. So there will always be some transition width and there will always be some stop band attenuation which you can reduce further. So there is one more method that is possible, that is called as frequency sampling method. In case of frequency sampling method, what we do is we assume that there will be some small ripple in the pass band. We assume that there will be some stop band oscillations. That is what we call it as the Gibbs phenomena. And these stop band attenuations, we try to select the particular points where we want to have the desired response. So we will select the frequency points as per the desired response. These selected frequency points will then become the DFT coefficients, and then you try to take inverse DFT to get the filter design. So in this case, we don't have to truncate it and then make it causal. Those things will not be required, because considering the actual response, we try to fix up the frequency points or select the frequency point. So we'll consider this frequency sampling method in detail in the next video. This is the you can say first step in the adaptive filter design. So normally in the practical situations, we'll be designing the filters as the adaptive filters, and the first step in the adaptive filter design will be the frequency sampling method. So we'll continue with this in the